Hello everyone, welcome back to the mechanical vibrations tutorial. Today we are going to start a new topic, which is the vibration under general periodic force. So let's begin. So as you may remember from before, in many force vibration cases that we had before, the force was in the form of a cosine function or a sine function, which means that the force is a harmonic function. However, in many real cases, the force is not necessarily harmonic, but it is periodic. So for example, imagine we have the mass spring system, and actually there is a damping in the system as well. So we have C, K, and M, and the force applied to the system as Ft, and for short this is X, our motion or degree of freedom. So imagine this force F is not harmonic, but it is periodic. For example, if we have, say for example, a triangular shape force applied this way, and this is actually tau, or we have another types of force, like we have a rectangular force shape which is applied periodically. So as you see here, these are some cases that the force applied to the system is periodic, but it is not harmonic. There are some real cases and examples that I can tell you. For example, if there is a ratchet design or a cam design. So imagine, for example, let's forget about damping. There is a mass spring system, and the mass is rested on a sort of like a cam shape, and which is rotating this way, and this is caused a sort of periodic force which is applied to the system, but the force is not harmonic. So as you can see, you can imagine other examples and cases that the force is not harmonic, but it is periodic. So for all these types of systems, again, we have our general equation of motion, mx double dot plus cx dot plus kx equal to Ft. But the thing is, the force Ft is not just a sine or cos function, and we have to figure out how to solve the problem. So in order to find the response for such systems, we can use the Fourier series. In fact, if you don't remember Fourier series, you need to go to your calculus and math courses and review them again. How we can deal with such systems? We need to find the Fourier series or Fourier transformation of the force Ft. So as you know, any periodic function can be represented as Fourier series, right? Again, you can remember that from your calculus courses, or you need to review that. So for example, Ft can be written as A naught divided by 2 plus sigma j from 1 to infinity A j cos j omega t plus sigma j from 1, this is j, to infinity b j sine j omega t, right? So this is the Fourier representation of a periodic force, and we just need to find A naught, AJ, and BJ. So fortunately, we can find them based on the existing relationships in the math and Fourier series, so you don't have to find it from scratch. So in fact, for example, for AJ, it is equal to 2 over tau from 0 to tau Ft, or Ft cos j omega t dt, and for BJ is 2 over tau from 0 to tau Ft sine j omega t dt. And for A naught, it's even easier. You can simply find it by taking the integral of the Ft plus some other constant that you need to apply to the system. So in fact, A naught can be found simply by finding this integral, which is equal to 2 over tau from 0 to tau Ft dt. So you may ask what function we use for Ft. For Ft, we need to take the function appears in one period. So for example, imagine this is Ft and we have t and it is periodic. like this. For example, we have bumps repeated, so we use the function only in one period to find the integral and the constant, or basically the coefficients of a naught, aj, and bj. So again, we represent our periodic force in the form of Fourier series, and then we can simply substitute this Fourier series into our equation of motion. So imagine we have m x double dot plus cx dot plus kx equals to ft, and ft is now a combination of multiple harmonic terms. So we can use the superposition, which means that we find the response for each component and then sum them up. So we are not supposed to do it here, but I just explained so that you know how we can find the response of the system. So ft is a function of multiple harmonic terms because it is a series of cos and sine function plus a constant, which is a naught divided by 2, and then we find the response for each one, and then we use the superposition, which means that we sum up all the responses. But we don't have to do it here. We basically know the response of the system, and as we talk about the response, we talk about the particular response or the steady state. Again, remember, when we have a damping, the transient response will go away after a short period of time, or it could be longer depending on the damping constant. But what we do care about such systems is the steady state or the private solution. So xp, the steady state response, is gonna be a naught 2k plus sigma j from 1 to infinity a j divided by k, the whole thing divided by the square root of 1 minus j squared r squared plus 2 zeta j r squared cos j omega t minus phi plus sigma j from 1 to infinity bj divided by k sigma 1 minus j squared r squared plus 2 j zeta or zeta j, doesn't matter, r squared sine j omega t minus phi j. So the phi is also dependent to j. So as you see, I want to explain more on this equation. So these two equations are basically the summations of the response for each j. Why we have it for each j? Because ft was a function of different j's. That's why you have it in the form of series, right? And I should mention that as you can look into these equations, everything is clear. We know r, which is basically omega over omega n. We know zeta, which is basically, you know, our damping constant or damping ratio, C over C critical, and C critical is a function of, you know, we can find it based on K and M. So the only unknowns in this response is A naught, AJ, and BJ, and we found them in the previous slide, right? Which are actually from the FT. So the only thing left is basically phi j, which is also equal to the tan inverse of 2 zeta j r divided by 1 minus j squared r squared. So as you see, everything is the function of j. And why? Because it is the superposition of all the responses, all the terms related to j, right? So that's why you have these two sigmas defined in this problem. So what you need to do in these types of problems is pretty simple. You need to find the function of ft in one period, and then find a naught, aj, and bj, and then plug it in to this equation to find the steady state response. So you don't have to do anything else because everything else is known, like K, R, C are pretty simple. We can find the expression for A0, AJ, and BJ, and phi j to find the steady state response of the system. So what I'm gonna do now is to solve one example, and then you will see how we can basically apply this method to the problem. I should mention that these types of problems, when the force is periodic but not harmonic, needs a lot of math and calculations and integration. So if you want to solve these types of problems, or if you want to see like how I use these types of solution procedures, you need to review your math and calculus contents like integration by part, Fourier series, and so on. Okay, so let's have one example and see how we can use this method. Okay, so this is a case that the applied force is basically a sort of, let's go over the problem and see what it says. So we are looking for the steady state response of the system, and the system is viscously damped, and the force function is as shown here. So in fact we have m x double dot plus cx dot plus kx equal to ft, but force F is periodic but non-harmonic, and we have this is tau and F naught is the amplitude. So what does it mean? Like, how can we sort of show this example, or basically represent these types of force? So imagine, for example, you have a sort of mass spring system. So we have a spring and a damping and the mass, so CK, and a force applied to the system follows a cam with a sort of helical shape. So imagine if I want to draw it, this force, like this force F, is applied through a cam like this. If I can present it very well, so like this cam rotates along this axis. So what happens is, sorry for my drawing, it's like a helical shape. So as the system like this rotates, it starts from like a very small amplitude, or starting from 0, and then increases and then goes to a certain amount, which is the maximum force in here, and then it jumps or drops down to the starting point, which is here, right? So this can mimic the type of force that we showed in this, basically in this graph, using a cam design, right? Or if I want to show it in a better way, so imagine this is the center of rotation for the cam, and the cam follows a sort of helical shape, right? Something like this. Okay, so this can basically mimic, and the rotation is this way or that way, doesn't matter. It can mimic these types of force, right? So for each period, we know that Ft is pretty simple and follows a linear function, which is F naught T divided by tau. So F naught and tau are known, and T is like time, right? And T changes from 0 to tau for each period. So keep this in mind, because we need that to find our coefficients A naught, AJ, and BJ, and then plug it into the equation. So let's do that. Okay, now we found basically the function of A, and we can simply find the coefficients like A naught, AJ, and BJ, the standard method. So what is A naught? So for A naught is basically we take the integral over the period for Ft dt, and if we plug in basically the function for Ft, so A naught would be 2 tau from 0 to tau F naught tau T dt. So this is a constant part, we can take it out, which gives us 2 F naught divided by tau squared from 0 to tau T dt. And I'm pretty sure that you know how to find this integral, because it's pretty easy. So A naught would be 2 F naught divided by, so this is f naught tau squared. So the integral of t is t squared divided by 2 from 0 to tau. So if we plug in the upper bound and lower bound, we can simply find f naught. So it's gonna be 2 f naught. I'm gonna do it here for this one, just for showing how we can perform the process. So we plug in tau and then we plug in 0. So we get a naught equal to f naught. So see, a naught is a function of the amplitude of the force, right? So basically this one cancel this one and this cancel that, and we get f naught. Okay, so we found the first unknown parameter of the system, which is basically a naught. Now we need to find the other one, which is basically the aj. So what is aj? aj is equal to 2 over tau 0 to tau ft cos j omega t dt. So for aj we have it's equal to 2 tau 0 to tau f naught divided by tau, right? You remember that? T cos j omega t dt. We can take this part out, so we have a j 2 f naught tau squared 0 to tau t cos j omega t dt. So as you can see, now we ended up into a bit more complicated integral, which we have t and a cos function. I'm sure that you can find some references or handbooks to deal with these types of integrals, but for the case of showing how we can solve this equation, I want to use integration by part for this case. So if we have integration by part, just a review on that. So if you remember, if we have the integral of u dv, it is equal to u v minus integral of v du. So we need to properly have u and dv in our problem, and then we can use this formula, right? So for this case, so I'm gonna write it again. So we ended up to a j is equal to 2 f naught tau squared integral of 0 to tau t cos j omega t dt. So I define u, let me do it again. So I want to define u and v properly. So u is equal to t and dv is equal to cos j omega t dt. So from here du is gonna be dt, and from here v is gonna be 1 over j omega sine j omega t, right? If you take the derivative of this, you find dv, right? So now it's pretty easy. We can plug it into our formula for integration by parts. So a j is gonna be 2 f naught tau squared. I know it's a little bit of math, but you have to basically do it to find the final response of the system. So we have uv, so we have u times v, 1 over j omega sine j omega t, right, minus the integral of v du. But this part is okay, so we need to plug in 0 to tau here, minus what is the integral of v du from 0 to tau. V, we know that, and du is just dt, so we have 1 over j omega sine j omega t dt, right? So this is actually dt, or I have to write it again, but again, the purpose is not to find the integral, is to know how to use that. So I hope you can basically review your math courses and find that in there, or you can find more information in our channel on taking integral or so. So this is dt, right? Now we have everything set. We can find aj by plugging the upper bound and lower bounds. So if we do this, we can basically find the response of the system. So, or actually aj first. So we get aj equal to 2f0 tau squared. So we have, if I plug in the upper bound and lower bound and simplify that, we have basically the two parts in here and there, and this part is pretty easy to find the integral because we only have a sine function. We get 0 minus 0, and then for this part we have minus 1 minus 1, right? This part is pretty easy to find the integral, right? Because we only have a sine inside the dt, right? So we get aj equal to 0 simply, right? So we found aj equal to 0. Now the rest is bj, and we have to find basically bj in the system. So to find bj, we have bj equal to 2 tau from 0 to tau f naught tau t, which is ft, right? Sine j omega t dt. Again, we have bj equal to 2 f naught tau squared from 0 to tau t sine j omega t dt. So we have u as t and du is equal to dt. So again, integration by part, and we have dv equal to sine j omega t dt. So v is 1 over j omega t cos omega t and minus, right? So this is dv. So we can use the integration by parts simply as I showed before. So I want to do that here because you will see that bj is not 0 here. So what we get here is bj is equal to, I want to expand it, is equal to 2 f naught tau squared times, so we have from integration by part uv, which is 1 minus j omega cos j omega t from 0 to tau, minus the second part v du, the integral from 0 to tau, v is minus 1 over j omega cos j omega t, and du, which is dt here. So again, this part is pretty simple to find the integral. This is just a substitution, and this one is pretty simple to find the integral because the cos function, we can find it based on sine function. So let me do that and see what we have here. This is equal to 2 f naught divided by tau squared. So for the first part, we basically have t, I'm gonna write it again, doesn't matter, t and minus 1 j omega cos j omega t from 0 to tau, right? And this part of integral is plus 1 over j squared, j omega squared sine j omega t from 0 to tau, right? Now we need to plug in the upper bound and the lower bound, and remember tau is 2 pi over omega. I didn't say that in the previous slide, but remember, when we want to plug in, we can simply convert omega to tau or tau to omega. So basically omega is 2 pi over tau. So in all these omegas, in here, we can basically use the relationship for tau. So once we plug in tau and t, we can further simplify it. We have to do this for the previous slide as well, so just to keep it in mind. Okay, so now what is left is the substitution in the previous integral. So bj is gonna be basically 2 f naught tau naught times minus tau 2 pi j times tau minus 0, and the second part, the sine part, basically is 0 because you have sine of like a function over a period, right, which is 0. So this is what's left from substitution, and it gives us bj as, so bj as minus f naught over pi j. So as you see, bj is a function of j. So let's see what we have so far. So we found a naught as f naught, we found a j as 0, and we found bj as minus f naught divided by pi j, right? So as you can see, we found what we need for this problem. So the rest of it is just substitution for the standard function we have for xp. So for xpt, our steady state response, it was, you remember that, right? I just don't want to write it. We had a naught divided by 2k plus a sigma of say for example a j times a function that I don't want to write it, something times basically cos j omega t minus phi j plus sigma bj and a function sine j omega t minus phi j, right? So this is phi j, sorry, right? So I'm sure that you know this equation. It's just k divided by square root of, you know, something as a function of r and zeta, right? So if we look at this equation, we notice that this part is 0, so the whole sigma here is 0. Why? Because aj is 0. So we can simply plug in rest. So x p t is equal to f naught divided by 2k, so a naught was f naught, plus sigma bj is minus f naught divided by pi j, j varies from 1 to infinity, times the function we have is k divided by square root of, I'm sure that you can remember that, or you can find it in my previous slides, squared plus 2j zeta r squared, right, times cosine j omega t minus phi j. So let me put the whole thing in a bracket. So this is like the whole thing inside the series. So we basically found the steady state response of the system. As you see, everything is known. The last thing that we need to find is phi j. So phi j, we know the equation from before, so it's equal to the tan inverse of 2 zeta j r divided by 1 minus j squared r squared. So it is not something that we don't know how to find that, because we already know r and zeta for a sort of, you know, single degree of freedom system, and like the rest, j is just the variable or just the parameter we have here, right? So as you see, we found the response of the system, the steady state response. So the art of this problem is how to find a naught, aj and bj, and in many standard functions you will see that either aj or bj or even a naught would be 0, depending on the function of ft, or there could be the cases that none of them are 0. So but the you know, the point is to know if you find aj, bj and a naught, you can find the steady state response simply, and the rest is just substitution. so you don't have to be worried about the rest of the problem. So in fact, the response of a single degree of freedom system under any periodic force can be simply found through this process, and just by finding the Fourier series components of the force, for basically taking the force function in one period, right? So you will see in the future that we have other cases that the force is not necessarily even periodic, and we have to find another method to find the response of the system. So I hope you get the idea on how to find the response of a single degree of freedom system under a periodic but non-harmonic excitation. Remember, in many cases, you need to simplify the system first, find equivalent mass, equivalent damping, and equivalent stiffness, then apply this procedure. So in many cases, the system is not a simple mass spring damping system. You need to simplify it, then apply this procedure if the force is not harmonic but it is periodic. I hope you enjoyed the video, and stay tuned for the next videos.